Well, it's always nice to talk about something that you're really fascinated in, and I've spent most of my research career working on this sort of topic, instabilities and bifurcations, which I'm looking forward to explaining a little bit today. We've got the Tacoma Bridge up there, just to show you what happened when a really big bridge wasn't designed correctly and simply blew down. I'm going to start with an experiment, and I'm going to ask somebody to help me with the experiment. I want to make a sort of start off with a big bang. Come on, you've just volunteered. What we've got here is an arch, and it's an arch made of steel strip. I'm going to want you to pour some sand into that. I think come around the back. Right, yeah, okay. I'll tell you when to start. Okay, so this is a steel strip. It's very springy steel. The steel is not going to fail. There's not going to be no failure of the material, but the system's going to become unstable, I hope. It's pinned with ball bearings at the ends, and we're going to run some sand in. Right. Okay, good. Well, we'll just keep going. Then it's nagging, it's not coming out of the bottom. Oh, yes, it is. Keep going, keep going. It may just want a little assistance. It's not actually going down, is it? Soon sort that out. Just 1 minute. I'll put my glasses on. When things get critical, I put my glasses on.
It's blocked up here.
Okay. We shall solve this in a minute. This is just to show you how real it all is. Okay, we'll let it run. It's running now. Just leave it. Just leave it. Okay. So we're gradually increasing the load on this structure. Sand's running in. We might even want some more sand. The acute observer will notice that it's losing its symmetry, and this is an example of a symmetry breaking bifurcation. There we go. And now what have you done? Now look what you've done. Thank you. Okay, so that's, no, the sand's still coming. This is an example of something becoming unstable. The material hasn't failed, but it's jumped through. Not a good thing if this is a bridge. And of course, you notice that in order to get through, it has to go into, it has to woggle its way through. There's no way it would stay symmetric. So it sort of woggles its way through like that. Okay. Thank you very much. So we'll now come off here. This is just a quick introduction of what I'm speaking about today. I'm going to look at buckling problems, some symmetry breaking problems. That was a symmetry breaking problem we were looking at then, actually. If you can imagine it was loaded exactly symmetrically, that breaks the symmetry. Floating logs, I've got offering a prize if you can tell me how logs float. I'll give you a preview of that one. I want to know how this is going to float. It's a bit of maple. It's a square cross-section maple log. No tricks, homogeneous, uniform. How does it float? And then I'm going to look at some oscillatory instabilities, rather like the Tacoma Bridge that we've been looking at, and then some problems in the stability of motion. Okay. This is just then a summary of what we've seen. An experiment on an arch, introduction to buckling. This is what civil engineers would call a pin-ended elastic arch. And as we saw, it starts off symmetric, it ends symmetrically, but has to pass through this non-symmetric position halfway through. Okay, so every book that you read about stability starts with a ball rolling on a surface, and the reason is very good. It's absolutely the best way of thinking about it. Firstly, there are two equilibrium states here. One is at the bottom of the well, where it stays, if put, and the other is at the top, where it would stay if you were very, very careful, and it was an absolutely perfect world and there were no disturbances. So these are two equilibrium states, but you perceive immediately that this one is stable in the sense that if it's given a little knock, it stays there. This one, if you could balance it, is unstable because even if you balance it very carefully, in a real world where there would be vibrations coming from the floor, etc., even molecular vibrations, it would roll off. So that's just an illustration of the of equilibrium and the concept of stability. Now, in the world, conditions are always changing. For example, if we were thinking about a bridge, a convoy of lorries might come onto the bridge and increase its load. If we had an aeroplane, its speed might increase, and the wings would bear extra stress. So something will be changing, and whatever's changing, whatever's increasing, I'm going to call it a load. I mean, it was actually a load in the case of this test here, but let's just call it a load anyway. So a load might be the number of lorries on the bridge or the speed of the plane. And for our ball rolling on this surface, a load would be something that changed the landscape. In other words, it gradually distorted the landscape. And there's a rather easy way to distort the landscape, and that is just to tilt it. So what I'm going to do now is to show you how this is actually the simplest way you can get an instability, and it's in a very deep mathematical sense, this is the most typical way that you can have an instability. Essentially, the landscape changes. And as the landscape changes, the minimum is getting closer to the maximum. In other words, if you imagine that there'd been a ball sitting on the top as well, they're getting closer and closer together, and then suddenly off it goes. And that is actually the simplest way in which a system can fail. Oh, there's John Barrow's book. That was pure chance, actually. I just picked up a whole slab of books out of my shelf, and there was yours. One of your books, I might say. So this is what we've just witnessed, a fold instability in which the shape on which the ball is rolling started at the front here. We had a minimum, which is red, stable, and a maximum, green, unstable. As we tilted the landscape, they came together at this critical point, which is a fold, which is actually a horizontal point of inflection. And you're going to encounter that typically if you vary a control parameter. So P is our control parameter, our load if you like, and Q is position. There's an important concept of typicality here, which I'll just draw attention to. If somebody came up here and very quickly scribbled on the blackboard, you would find that you had maxima and minima, but you'd be very unlikely, in fact probability 0, would you have this fold point where you just had the curvature was just changing at the point at which you were horizontal. So it's typical to have an energy surface like that. It's not typical to have an equilibrium surface like this unless you're systematically varying a parameter. So systematically varying a parameter will bring you to this, in a sense, non-typical position. Okay, explosions of stars. Stars are also exploding all the time. This may be news to some. And in fact, our sun, which is also a star, of course, is going to explode one of these fine days. A million years or so, so I shouldn't get too worried about it. When a star runs out of its nuclear fuel, it starts to get very cold, and it collapses inwards under its own gravity, and may well collapse to a black hole, as is currently thought. These events are called supernova explosions, and about 10 are seen each year, though mainly by astronomers. They're probably rather faint. But there were two very well-known ones. One was observed by the Chinese in the Crab Nebula in the year 1054, and a star that had been very bright for years and years and years suddenly became very, very bright. It had been faint for many years. It suddenly became very, very bright. Could even be seen during the daytime. So for 23 days, it could be seen at midday. So you should keep your eyes open in the sky. A star that you're familiar with might suddenly become very bright. And this is a supernova event. Another one was seen by Tycho Brahe in 1572. These are recorded, you know, they made a note of this. And this is the remains of the Tycho Brahe event. there's an explosion. The material is flying out from the center of the star, and in the center is a neutron star. And this is where matter has collapsed to a very, very tight condition. For example, an apple on a neutron star would weigh 1 million tons. It's got enormous gravity. The material has really collapsed down to its neutron state. It's interesting that if a neutron star is spinning, it actually emits radio pulses, and it's very often called a pulsar. And the first ever pulsar was discovered here in Cambridge in 1967 by Jocelyn Bell, who's now a professor at Bath University. This is a simplified study of that effect made by Harrison using general relativity theory. And he showed that if you think of the control parameter now as being the mass of the star relative to the mass of the sun, so 1 would mean that the star had the same mass as the sun. And you might imagine that the mass is gradually increasing for the purposes of this discussion. And this is the density at the center, which gets up to ridiculous values, 10 to the 20 or something. So you have white dwarf stars, which are stable, but then if they get too heavy, they collapse and you get a jump probably to a black hole. You can have these neutron stars, which also can become unstable, and they jump again, probably to a black hole. So here are two folds. These are just the type of fold we've been talking about, where a stable solution curves over and becomes unstable. So I mentioned earlier symmetry breaking, and the first study of symmetry breaking was made by Leonhard Euler, a very famous Swiss mathematician. He made enormous contributions, and even though he went blind, he was able to continue his research, so he had such a prodigious memory. At one stage, he was invited by Frederick the Great to go to Berlin, and he wrote in a letter to a friend, "I can do just what I wish. The king calls me his professor, and I think I'm the happiest man in the world." Now, anybody like me who's had a research fellowship knows the feeling, somebody's actually giving you money to do what you want. So, Leonhard Euler. Now, the problem Euler studied was that of the buckling of a column, and he worked out in complete detail the behavior of a column. This is a column, and you compress it, and of course it buckles to one side. And you can see that it's a symmetry breaking problem because it could go either way. So this is breaking the symmetry. Euler worked out the deflections of this to enormous length. In fact, he studied the deflections that are so big that this point has actually gone past that point, and the thing is wrapped into a sort of a figure of 8. This sort of stuff is taught to civil engineers. Civil engineering undergraduates do a lot about this, and it's actually called Euler buckling. They say, we're doing Euler buckling today. So here's our column. We've got a load P on it, and the deflection is Q. If we plot load P against deflection Q, if we could make a perfect column, which of course we can't, if we made a perfect column, we'd have this red stable path, which would become unstable at a certain critical load, and there'd be a point of bifurcation, and the deflected path would come out and it would be stable. So this is an example of symmetry breaking. And this is an example of what we've got a pitchfork. So if you think about it, the red shape looks a little bit like a pitchfork. If you imagine the column were imperfect, in other words, if the column were a little bit bent to the left originally, and you tested that imperfect column, it would have a propensity to go this way, and you wouldn't hit the point of bifurcation. And that's going to be an important point that I'd like to explain in a few minutes.